Hi everybody, it is Sunday, December 1st, 2024. This is your SkillCheck10 comparing population proportions. In the first question, we're asking, are smokers at greater risk of heart disease compared to non-smokers? And so in this scenario, we're imagining that 102 adults were randomly selected. These are adults between ages 50 and 60. And these are adults who smoke. And we interview them and we find out that 21 of them were treated for heart disease. And then we take a second sample. In this case, we're interviewing 115 people who do not smoke. They're of the same age category. And we found that 14 were treated for heart disease. And so here we're going to let P1 represent the proportion of these Nova Scotian adults in this age category who smoke and have been treated for heart disease. And we're going to compare that with P2. It's the proportion who don't smoke and have been treated for heart disease. Now, of course, there's two ways to do the inference. One way is to make a confidence interval. The second way is to conduct a hypothesis test. In this scenario, we're first going to construct the confidence interval. So the first question is, assuming the conditions for the normal approximation are satisfied, construct a 95% confidence interval for the difference between those population parameters. And then we will draw conclusions. So we take our data. We can easily calculate the sample proportions P1 hat and P2 hat, and then the difference between those sample proportions. And so what this difference is showing us is that in the samples, about 8% more of the people in the smoker category were treated for heart disease compared to people in the non-smoker category. And so this is making it look like it's possible that smokers are more likely to have heart issues compared to non-smokers, talking about people between ages 50 and 60. But of course, seeing that the sample proportions, the difference between them is a positive number, isn't enough to make that conclusion. We have to take into account the uncertainty. And so that's what the confidence interval is all about. Let's calculate a measure of the uncertainty. That's the standard error for this random variable P1 hat minus P2 hat. Right, so square root, here we have, in our fraction here, we have P1 hat times 1 minus P1 hat over the sample size. That's for the smokers. And then we have P2 hat times 1 minus P2 hat over the sample size. That's for the non-smokers. So we just need to do this calculation. We'll have our measure of uncertainty. Now, there's two ways you can go about doing the calculation. And by the way, I want to emphasize, on the final exam, when you get a question like this, I want to see just exactly what you're seeing here. I want to see you write out the equation for the standard error with the values plugged in. After that, if you just give me the final calculation, that's fine. You can also, if you like, do the calculation step by step. Right? So if you want to do the calculation in one go, more or less, you need to know how to use the memory function on your calculator. Otherwise, if you want to go through step by step, that's okay too, but there's one issue. You have to know how to deal with the scientific notation. And so I'm just going to show you an example of that. Here, I'm going to calculate this second fraction. 0.1217 times 0.8783 equals, and then divided by the sample size. And here's what we get: 9.29 a bunch of decimals, a bunch of digits. And at the end we got this minus 4, e minus 4. So what is this minus 4 telling us? It's telling us that the 9 goes in the fourth decimal place. And so in other words, it tells us that the final answer that we're going to use for our calculation is 0.0009. So notice two things. One, if I'm doing the calculation step by step, I'm maintaining 4 decimal places. That's the way we agreed to do it. That way you can avoid any problems with rounding. Secondly, the scientific notation is telling us that the 9, this first digit that the calculator gave us, goes in the fourth decimal place. So you see 0009, that's the fourth decimal place. So we don't need to write any of the other digits because we're rounding to 4 decimal places anyway. So this is how you deal with the scientific notation. So continuing, the next step, I'd like to calculate the margin of error. And once I have that, I'll go ahead and calculate the bounds of my confidence interval. I find it's just easier to do it that way. So let's do that margin of error. We need to remember the critical value for a 95% interval is 1.96. And the standard error that we calculated on the previous slide, 0.0012. So our margin of error is 0.0024. So we have our point estimate and we have our margin of error. We just go point estimate plus or minus margin of error. We get the bounds of our confidence interval. Now, what do you notice right away about this interval? It is positive, meaning the lower and upper bound are both bigger than 0. So that's telling us something. So let's see. The first part of the conclusion is this: assuming the conditions for the normal approximation hold, we are 95% confident that the proportion of smokers in Nova Scotia in this age category who have been treated for heart disease is between 8.18 and 8.66% greater than the proportion of non-smokers in this age category who have been treated for heart disease. And so we can continue and say, since the interval is positive, we have evidence at the 95% level of confidence that smokers in Nova Scotia between 50 and 60 years of age are more likely to be treated for heart disease compared to non-smokers in the same age category. So when it comes to writing your conclusions on the final, I want to see both things. I want to see this sort of standard conclusion where you talk about, you say that the conditions, assuming the conditions hold, you mention your level of confidence, and then you go on and say what the confidence interval is telling you. And then you make a note whether 0 or not is in the interval, whether the interval is positive, or in some cases, whether the interval might be negative. And you make an interpretation based on whichever case it happens to be. So here the interval is positive, so I can make some interpretation about the difference between P1 and P2. And I can say the evidence shows that P1, the population proportion, is bigger than P2 by the amount that we talked about here. So that's the kind of answer I would like to see on the final. Second part of the question, as I said at the beginning, of course, there are two ways to do inferences. One way is to construct a confidence interval. The second way is to conduct a hypothesis test. So here we're going to conduct a hypothesis test. We already know what P1 and P2 represent. And so we just need to write out what our hypotheses are. So the null hypothesis is always that the two proportions are equal. So in this kind of scenario where you're comparing two population proportions, this will always be the null hypothesis for our purposes. In this case, the alternative is an upper tail test because we're asking whether or not P1 is bigger than P2. Smokers are more likely to be treated for heart disease. So there's your alternative hypothesis. So next we need to calculate the pooled sample proportion and the pooled standard error for our for our random variable P1 hat minus P2 hat. And why do we need to go through this trouble? Because we need a measure of uncertainty so that we can standardize our point estimate. So going back to the data, the pooled value is just on top the total number of individuals who were treated for heart disease. On bottom, the total number of individuals in the study, in both samples added together. And remember what this p-pooled is. Under the null hypothesis, we assume that the two population parameters, P1 and P2, are equal to each other. And so this p-pooled is our best estimate of that common proportion. And why can we do this? Why can we calculate p-pooled and use it in our calculations? Because we start with the assumption that the null hypothesis is true. So here p-pooled is just a bit more than 16%. What do we do with that? Well, we're going to plug that in to our calculation for the uncertainty, a measure of the uncertainty. So here we use p-pooled times q-pooled in both fractions. The only difference is the sample size. And so we plug numbers in like this. In this case, when we do the calculation, we don't get scientific notation anywhere, and so we're good. We can easily do this step by step, and in the end, we get 0.05. So after rounding, it just turns out by coincidence, our standard error pooled happens to be exactly 0.05. Right, so before we calculate our test statistic, let's agree on what the decision rule is. If it's a 5% test, then our decision rule is going to be based on a cutoff value that puts 5% in that upper tail. And so going back to the values for confidence, we know that a 90% confidence interval puts 5% in the upper and in the lower tails. And so the critical value is going to correspond to that 90% interval, 1.645. So our rejection region is here, marked in red, and our decision rule is we're going to reject a null if the test statistic or the z-score is greater than 1.645. Okay, so now we're going to calculate the test statistic. No problems there. We're going to compare the observed difference, P1 hat minus P2 hat. That's our point estimate minus the mean value under the null, and divided by the measure of uncertainty, the pooled standard error. So just to remind ourselves, this is our point estimate, 0.0842. There's our pooled standard error. And so we get a test statistic of 1.684. So clearly, we can reject the null hypothesis at the 5% level of significance because the test statistic is 1.68, which is greater than the critical value for the test, 1.645. So we're going to reject. I just want to remind you something. That is, remember that the probability that this is a false rejection, or in other words, a type 1 error, is equal to the level of significance of the test. That's worth remembering. I'm sure there's going to be a multiple choice question somewhere on the final, maybe a long answer question even, where you need to remember this. So I just want to remind you of that. What's our final conclusion? We conclude that there is evidence at the 5% level of significance to support the alternative hypothesis that smokers in Nova Scotia in this age category are more likely to be treated for heart disease compared to non-smokers in the same age category. Last thing, we need to assess the strength of the evidence supporting the alternative hypothesis. And so to do that, we're going to calculate a p-value. We need to go to the Z table, look up our test statistic 1.68. We see that the area to the left of that test statistic is 0.9535, and so that means the area to the right in the upper tail is 1 minus that. It's 0.0465. That's our p-value. So what's the strength of the evidence? That p-value falls into the moderate range. It's more than 1%, but it is less than 5%. So the strength of the evidence supporting the alternative hypothesis is moderate. So moving on to scenario 2. In this scenario, we're imagining that there's a very large university. We're assuming it has thousands of statistics students. And I should mention Dalhousie University, first-year stats classes, typically there's over 1,000 students. So this is not unrealistic. But here we're assuming that we take a random sample of 325 of those students who wrote a practice exam, and of those, 12% failed the real final. And then 495 randomly selected students who didn't write the practice exam, 18.8% of them failed. And the question is, does the data provide evidence that completing the practice exam reduces the probability of failing the real final exam? So a big difference between this question and the first one, here the number of successes and failures isn't provided. Instead, you're given a percentage, the percentage of students who failed the real final exam. And by the way, since we're counting those who failed, the proportion is the proportion who failed. Failing is considered to be the success, and passing is considered to be the failure. So that's a little bit contradictory, but that's okay. In the end, we need to know how to turn those percentages into counts so we can answer questions like this one. Show that the success-failure condition is satisfied. So all we need to do is take the sample size, multiply by the probability of success, in quotes, the probability of failing the real final, and we get a count. So in the first case, we find that 12% of 325 students is 39. So there was 39 students who completed the practice exam. 39 of them failed. 286 passed. Both of those numbers are bigger than 10. Likewise, of the students who didn't write the practice final, 18.8% of those students failed. That turns out to be 90 students. That leaves 405 who passed. Both of those numbers, again, are at least 10. And so since there are at least 10 successes and at least 10 failures in both samples, the success-failure condition is satisfied. So that's cool. Now, I didn't ask you here about the 10% condition. In this particular scenario, the 10% condition would probably need to be checked because the sample sizes are so big. And even if it's a very large university, there's probably only still a few thousand first-year stat students. But here we're not going to worry about the 10% condition. Okay, so let's state the null and alternative hypotheses. We need to define what our population parameters are. And so P1 is of the students who did the practice exam. P1 is the proportion who failed the real exam. P2 is of the students who did not do the practice exam. It's the proportion of them who failed the real exam. The null hypothesis in these scenarios is always that the two proportions are equal. In this case, we're wondering if writing the practice exam reduces the probability of failing the real exam, and so it becomes a lower tail test. Next, we're going to calculate the pooled sample proportion and the pooled standard error. Of course, we need a measure of uncertainty. And in these scenarios, the uncertainty is based on pooling the data. We can pool the data because under the null, we're assuming that the two population parameters, P1 and P2, we're assuming they're equal to each other. And so pooling the data gives us our best estimate of that common proportion. In this case, that estimate is about 16%, just a little bit less. So we can now use that to determine a measure of uncertainty in this scenario, plugging those into the equation for the standard error, the pooled standard error. So just looking at that calculation, let me just check to see if scientific notation arose as a problem here. So again, you have two ways to do these kinds of calculations. As long as you write this first part, this top equation, that's what I want to see on your final. After that, if you just now write down the final answer for the pooled standard error, I'm happy. You can do that if you use your memory function on your calculator. You can do the calculation all at once. If you want to do it in steps, that's okay as well, but you have to be sure you know how to deal with scientific notation because it might arise. And so here, I think the second ratio here, actually, it comes up in scientific notation. So let me just check that. So 0.1326. So that's equal to P pooled times 1 minus P pooled. I'm going to divide that by 495. And see, we get scientific notation. Now check it out. What that minus 4 is telling you is that this first digit, 2, goes in the fourth decimal place. But wait a minute. That 2, we can round up to a 3 because the next digit is 5 or more. It's a 6. So we're going to round that to 3 and put the 3 in the fourth decimal place. As you see here, 0.000, and in the fourth place, we put the 3. That's how you deal with the scientific notation. So completing that calculation, we get a standard error pooled 0.0265. So before we calculate our test statistic, we're going to determine what our decision rule is. We're conducting the test at the 1% level of significance. Whoa, I just noticed I have a typo up here. That should have said 1%. Yeah, I'm pretty sure on your assignment sheet it did say 1%. Okay, so let's make the diagram. At the 1% level of significance, we draw the standard normal distribution. We need a cutoff value that places 1% in the lower tail. Now this is a new one. I don't think we've seen the cutoff value for a 1% test before. So I'm going to tell you, and you can add this to your formula sheet, to make a 98% confidence interval, you need bounds that put 1% into each tail. That boundary plus or minus 2.33. And so given that, we can see that to put 1% into the lower tail, we're going to use minus 2.33. Our rejection region is marked in red. Our decision rule is we're going to reject the null if the test statistic or the z-score is less than minus 2.33. So now we're ready to calculate the test statistic. That's pretty straightforward. We look at the observed difference in those proportions minus what we assume is the case under the null, which is 0, and we divide by our measure of uncertainty. So we need to calculate P1 hat minus P2 hat. We can do that directly from the proportions given in this scenario. So it turns out the difference is minus 0.0618, and the standard error pooled is 0.0265, and so when we put those together, we get a test statistic of minus 2.33. Now, what do you think of that test statistic? What do you notice about it? It's exactly the same as our critical value. Now remember, our rule is we're going to reject if our test statistic is to the left of the critical value. But after rounding, we get a test statistic that's exactly the same as our critical value. And so we cannot reject the null hypothesis at the 1% level of significance because the test statistic is not less than the critical value. Just to remind you, here we could be making a type 2 error because we didn't reject, and that could be a mistake. That's a type 2 error or a false negative. Now, I want to point something out here. Even though we didn't reject, a 1% test is a stringent test. And that's because what we're basically saying when we set the level of significance to 1%, we're saying we're willing to take a 1% chance of falsely rejecting the null. So that's quite stringent as a test. Here on the bottom, you can see what I'm saying is we can nevertheless, even though we didn't reject the null, we can nevertheless conclude that there is moderate to strong evidence to support the alternative hypothesis that the proportion of students who will fail the final exam is less amongst those who wrote the practice final exam. Now, why am I using the words strong to moderate? To answer that, we need to consider what the p-value is for this test statistic. So here the p-value does not require calculation because we know the area to the left of minus 2.33 is 1%. So the p-value is 1%. And when you look at our table with the adjectives to describe the strength of the evidence in support of the alternative, you can see that 1% is on the boundary between strong and moderate. And so here we can say, yeah, even though we didn't reject the null hypothesis, there's still moderate to strong evidence in support of the alternative. We didn't reject because we set a stringent value for our level of significance, but there's still evidence in favor of the alternative. Okay, now the final part here, we're going to now go back to the other side of the inferential coin. We're going to construct a confidence interval. And to do that, we have to calculate our measure of uncertainty. So that's the standard error of P1 hat minus P2 hat. So we already have our point estimate, minus 0.0618. We know the critical value for a 95% confidence interval is 1.96. We just need to calculate that standard error. So pulling up our numbers, we plug those in and we go ahead and do the calculation. Here, let me check to see once more if we have an issue with scientific notation. So let's just do both of them this time. So the first fraction is 0.12 times 0.88 equals divided by sample size, 325. Yeah, so this one has a scientific notation. This first fraction comes out when you do the calculation in scientific notation. I don't remember that being the case, so I'm going to double check to make sure I did the calculation correctly. So 0.12 times 0.88 divided by 325. Yeah, okay, so what is this telling us? It's telling us that the number we put here has a 3 in the 4th decimal place, and so it's going to look like this. It's got a 3 in the 4th decimal place. It turns out if you do the second fraction here, you get the same result when you round to 4 decimal places. So it also comes out in scientific notation with a -4, telling you to put a 3 in the 4th decimal place. Let me just do that just to be sure as one final example. So we go 0.1818 times 0.8182 equals, and then divide by 495. Right, so you can see there's a 3 in the 4th decimal place as I have it written here. So that's the way you deal with this scientific notation. So putting those numbers together, whoops, that was too fast, we get a standard error of 0.0245. That's our measure of uncertainty. So now we can construct our confidence interval, calculating the margin of error, and then taking our point estimate plus or minus that margin of error. We get this interval. Now remember, when we conducted a hypothesis test at that stringent level of what's it called again? Level of significance, right? A 1% level of significance, very stringent, we failed to reject the null, although just barely, we failed to reject it. Here, we're constructing a 95% confidence interval. Because it's 95%, that's a little bit less stringent. And you can see that our interval is negative. What's that telling us? That's telling us we have evidence that students who do the practice final have a slightly smaller chance of failing the real exam compared to students who do not do the practice final. And so that's the conclusion we're going to draw. So assuming the conditions for the normal approximation hold, we are 95% confident that for a student who did the practice exam, the probability that they will fail the real exam is between 10.98 and 1.38% less than that for a student who did not do the practice exam. And we can also point out that there's evidence at the 95% level of confidence that writing the practice exam increases the probability of passing the real exam because the interval is negative. Let me add that in there. Because the interval, let's say the confidence interval, let's just say CI, the confidence interval is negative. Whoop. And what I mean by negative is both the lower bound and upper bound are both less than 0. So 0 is not in there, and the true difference is some negative value. Okay, so I think that brings us to the end. Yes, it does. So thank you for watching. I hope this helped you. I hope it helped you enough that you can get this right on the final, because you know you're going to see both of these kinds of questions. What I mean is you're going to see a comparison of P1 and P2, two population proportions. You're going to see the hypothesis test. You're going to see a confidence interval. So wouldn't hurt to watch this video again, maybe a few days before the final. If you have any questions, you can send me an email. You can put it in the comments. You can ask me in class when I see you this week.